We want to create a buck converter for this motor right here to drive it with a battery pack. So let's look at what we're trying to do. So we have the motor, and you see the motor is modeled as a 2.5 ohm resistor in series with a 1 millihenry inductor. And we want to use the Arduino that has a 0 or 5 volts and a 980 hertz supply. And then here is our battery pack supply. Now the thing is that this Arduino runs fairly slow. So we want to use the Arduino to make a DC voltage and then use a high frequency PWM signal in order to drive everything. So let's start with figuring out what we need to do. We're going to start with creating the PWM signal. So what we have is we have our Arduino, which has a 5-volt PWM signal, and we want to convert it into a DC signal. So what we're going to do is we are going to use this circuit, and that's basically going to filter off the Arduino, and then we're going to create a sawtooth signal. And then we're going to run these two signals into a comparator to create the PWM signal. Okay, so in order to do this, you see that we are going to come in here and we're going to use the LTC 6702 comparator. So here's the 6702 comparator, and if we look through, you see it has a supply voltage up to 6 volts. So we're just going to use a 5-volt supply. So we're going to come in here and might as well make this voltage signal right here to be about a 1-volt signal, and then we're going to adjust this down to whatever it needs to be. Okay, so let's go back and see what we're trying to do. So we're trying to produce a 5 amp signal across that 2.5 ohm resistor. The first thing we need to do is figure out what our duty cycle needs to be. So our V out needs to be the 2.5 ohms times the 5 amps. So if we calculate what that is, 2.5 times 5. So we need an output voltage of 12.5 volts. Now our duty cycle is going to be equal to V out over V in, which is going to be 12.5 divided by this 29.6. And then that comes out to 0.422 volts. So we want our sawtooth to go between 0 and 1 volts, and we want to make this DC voltage to go from this 5 volts down to 0.422 volts. Okay, so let's start with that part first. So we're going to have our voltage source. This is going to be our Arduino source. And so it's going to change from 0 to 5 volts. Okay, it has a frequency of 980. So it's going to have a period of 1.02 milliseconds. And we want a duty cycle of 0.42. So we want the on time, oops, that was supposed to be the period. 1.02 milli, and we want an on time of 0.43 milli and then fill these in. So 0, let's do a 1 nanosecond, 1 nanosecond. Okay, so here is our PWM signal coming out of our Arduino. And then we are going to do an RC filter in order to filter it. So let's just pick a 1 micro and pick a 1 kilohertz and see how this turns out. So we're going to run this. And so you see we're kind of filtering this down. It has an average value of 2 volts. We need this a lot smaller. Oops. I did my calculation wrong. So we wanted 0.42 volts out of the 5. So we want 0.42 divided by 5 times the 1.02 milliseconds. So we want 0.086 milliseconds. Okay, now let's try that. Okay, so that's closer. So you see the average point in here, we're around our 0.42 volts that we wanted. This has a little bit too much ripple, so we either need to increase, it's an RC time constant, so we either need to increase our capacitance or increase our resistance. So let's go up to 10 micro. Let's see what that looks like. So you can kind of see we get a little bit of ripple here, but it's not too bad. So we're around the 0.42. So now this is going to be our new signal. And now this is going to be our DC signal. And now we need our sawtooth signal. So now we add in our voltage source for our sawtooth. And then this one is going to be a sawtooth. So this is going to go from 0 to 1 volt. And we need to figure out what frequency we want. So let's go back to our calculation. And this one already has some inductance built in, so it would be nice to try and use that inductance so that we don't have to add in another inductance, another inductor. We'll just use the inductance of the motor to get it all to work out. So let's go back and look at our equation for current ripple. So our current ripple equation is equal to V in times D times 1 minus D times TS over L. And what we're going to do is we're just going to adjust our frequency to get it to work out. Well, rather than, so we're going to come in here and we're going to plug in all of our numbers. So we're going to have TS is equal to delta I times L over V in times D times 1 minus D, which is equal to, we want a current ripple of 0.5 amps. We have a inductance of 1 millihenry. And we had a voltage of 29.6, and we had 0.422 and 1 minus 0.422. And so then this equals, so this equals 69.9 well, let's just do 69 microseconds. Okay, so now we're going to come back here. And this is going to be 0, 69 microseconds, and 69 microseconds. Okay, so now we're going to put in our comparator here. So we're going to go grab our comparator, and that was the LTC6702. There it is right there. And so we're going to come in here and grab our comparator. Now this one is ground. We need a voltage source. We're just going to use a 5-volt voltage source. Okay. So now if we run this, we can see that if I look at this voltage, it looks approximately like, so you see here are the cross points, and so we filtered out this 5-volt to produce this small volt, reference it relative to our sawtooth, and then we create this PWM signal that should have a duty cycle of around 0.42 and a period of with 69 microseconds. Okay, so now we have our PWM signal. Now we need to convert this over to our full system. Okay, so let's add in the rest of the pieces for our full system. So we're going to start with our power supply, 29.6 volts. We're going to have our transistor. And we're using the IRF 530. And we're going to go grab a diode. Now we're doing about 10 amps, so we're just going to grab a Schottky diode that can handle about 10 amps. This one looks, I don't know, any of these look good. Okay. And then we're going to have in our inductor for our motor and the resistance for our motor. Okay. This was 1 millihenry. This was 2.5 ohms. And then we connect this to here. Okay, so now this is a high side switch, and here's our PWM. We have to get this PWM to control this. Now, if we're doing a gate driver, you see we have to move the gate driver all the way up to the 29 volts. The gate driver can't handle 29 volts, so we need a different type of gate driver. So this is a high side switch. So what we're going to do is we are going to use a high side gate driver. So we can see here that we have here is an LTC 4440 high side gate driver. So let's go grab that. LTC 4440. Oh, there is our high side gate driver. And then we have all this. Well, ground I kind of understand. VCC I understand. This is probably input. I got to look up the rest. So we're going to go to here. And we're going to look up an LTC 4440. And here it is, a high speed, high voltage, high side gate driver. So here is basically what it does. So you basically see, oh, this is the boost. See this little diode and this little capacitor? So this is actually building a bootstrap converter. Okay, so you see that this TG is connected to the gate and the TS is connected to the source of the transistor, which is going to be between R2. We're going to be using a diode down here rather than another transistor. So I have to put a capacitor between the TS and the boost, and I put a diode between the VCC and the boost. We see that the VCC can go between 8 and 15. We want to get as much voltage across our gate to source, so we're just going to go ahead and use R15, and then we have our high voltage connected over here. So let's go and build this up. So this is the gate. So let's just move this down. So you see this connects across here. We're going to get a voltage source over here, which is going to be our lower power 15-volt voltage source. We're going to put a diode for our bootstrap part right here. We're also going to need a capacitor between our bootstrap and our TS, and then our TS connects over to here. Let's just move this down to make it a little prettier. Okay, and then this point here is ground. And then this part here is my input. So we're just going to take and align this up. With my input right here. Okay, so this is just a signal diode. So let's just grab the 4148. And then we need a value for this capacitor. Well, I'm not sure what to use, so I'm just going to go and scroll through here, see if they have any examples that have those diodes, those capacitors on there. You can kind of see this is showing what it looks like with all these level shifters. Oh, here's a big example. So let's grab one of these. It looks like they're using a 0.22 microfarad capacitor. So we'll just use that. Okay, so then we have the whole thing, and so what we see is that this is going to drive the gate of the MOSFET using our bootstrap capacitor, our bootstrap circuit, but it has gate drivers, so it's going to be much higher current, and then that takes this and switches. This is now my single pole double throw switch, and that's going to drive my inductor. Oh, we wanted one, not 1 Henry, 1 millihenry. Okay, let's go ahead and put our output for when we want to calculate efficiency. And put an input up here. And let's see how this works. So this is 50. Let's just run it like that and see what we get. Takes a little bit of long time, but it's going along pretty quick. Okay, so let's go through and look at all this. So there is our voltage signal. There is our sawtooth. And if we zoom in, you can kind of see there's our PWM signal. Okay, so then if I look at my gate, oh, there's my PWM signal. But you see that the gate now is going up to a higher voltage. So if I look at the gate to source, well, you see there is my 0 to 15. So it's putting the voltage across here of this voltage. I look at my voltage right here, and you see there is my nice voltage ripple. I can look at my current, and you see that this is what my current looks like. This is where it's building up. And then this is my ripple right here. You see it's around 5 amps and it has a peak-to-peak signal. And we can go and check our efficiency. So this is 58 watts, 65 watts. You see these are down in the milliwatts, down in the milliwatt, nanowatts, so everything's good. And then we check our currents. This one's in the microamps, this one's good, this one's low, so everything's really good, and I got it to work. We could, if my voltage level, my current level was off a little bit, then I would play around with the duty cycle of this one, or sorry, I would play around with the duty cycle of this one to move up my DC level, which is going to move up my PWM duty cycle. If my peak-to-peak ripple is worse, then I want to change the switching frequency, so I'm going to change the PWM of this one. And that's how we adjust everything.